Okay, can you hear me? Is it working? Yeah. So hello everybody. So my name is Sebastiano Pilati, and now I work at the University of Padua. And here you have a picture of Padua. And previously I was working in Trieste, so here you also have a picture of Trieste. Before starting with the presentation, I would like to thank very much the organizers for giving me the opportunity to come here. It's a great pleasure to come to Brazil. And I'm aware of the fact that this is the last talk of the morning session, so I will try to skip certain technicalities and not to take too much of your time. Here you see the list of collaborators. There are people both from Trieste and from my new workplace, Padua. So as you see from the title, I'm going to discuss about quantum Monte Carlo techniques, in particular about a specific kind of quantum Monte Carlo method, which here I call projective quantum Monte Carlo, mostly in the context of ultra-cold Fermi gases. Okay? But this title is actually a bit incomplete, because finally, given the audience, I decided to refocus a bit the talk. And in fact, the talk will be somehow divided into two parts. In the first part, I will indeed speak about... too far? Okay. I hope I don't have to repeat that. So in the first part, I will indeed speak about ultra-cold atoms, in particular about quantum magnetism in ultra-cold Fermi gases. And in the second part, I will kind of switch topic, and I will speak about quantum computing, which is a new topic for me, about a specific kind of quantum computing, which is called adiabatic quantum computing, which is about solving optimization problems at the end of the day. Okay? But the leitmotif between these two parts is the use of projective quantum Monte Carlo techniques. Okay? So there are two parts which are strongly related to each other, and I will try to convince you that quantum Monte Carlo methods are useful, very useful tools in both of these fields. So let me say just a few words about the systems that I'm going to discuss in the first part before turning into algorithm. So we will discuss about ultra-cold atoms. Perhaps you know that, so here we are dealing with extremely dilute gases, okay, where you have atoms which are the typical distance, which is of the order of 100 or 1,000 nanometers, okay. So it's a completely different regime, for example, compared to solid-state devices, which maybe some of you are more familiar with, which are much more dense, okay, so where the typical interatomic distance is of the order of 0.1 nanometer. Okay. So you might think that then these systems are boring because they're so diluted and the interaction doesn't do anything special, but we try to convince that this is not the case, not at all. And one of the reasons is that the systems are very, very, very cold, okay, so which means that the kinetic energy is extremely low, which means that the interaction energy, even though the system is dilute, might be comparable or even larger than the kinetic energy. So it might play the dominant role. So the interaction, well, probably you know that, I mean, in the very first approximation, when you have two atoms, you might describe their interaction by using something like a Lennard-Jones potential, okay? But these systems are extremely dilute, so that the typical length scales of these interatomic potential is actually much, much smaller than the typical distance between atoms, okay? But as we said, we are in a particular condition, so we are extremely low temperatures. At temperatures so low that the thermal wavelength is way, way larger than the length scale that characterizes the Lennard-Jones potential. Okay? This means that the details of this Lennard-Jones potential, they become completely irrelevant. Okay? So the interaction becomes purely quantum mechanical. You have to describe it using the theory of quantum scattering at low energies, which means that you can forget about the details of this potential. You can introduce some very simplistic models. We call them pseudo-potentials, which are characterized by just one length scale, one parameter, which is a length scale. It's called S-wave scatter length. It describes the strength of the interaction in the S-wave channel. Okay? Under typical natural conditions, this length scale might be smaller than the typical interatomic distance. So you can write an interaction parameter by writing the density m times this S-wave scatter length a to the third power. And this gives you an interaction parameter, which is typically very small. By using a technique which is called Fishbach Resonance, you can tune the value of this parameter a and make it large, even comparable to the typical interatomic distance, or even larger. Okay? So you can tune the system from a regime of very weak interactions to a regime of very strong interactions. Okay, so you might expect some interesting phenomena to take place when the interaction is very strong. Another technique which is used in the experiment to enhance somehow the role of the interaction and to see something interesting happening are called the optical lattices. Okay, so this is a technique where experimentalists use pair of counter-propagating laser waves that create a standing wave, a standing electromagnetic wave, which is perceived by the atoms as a periodic potential. Okay, so in this system you can have atoms or particles which are maybe strongly interacting, and they're also moving in a periodic potential which can be arranged to create a crystal structure. So in this simple example is a simple cubic 3D lattice. Okay. So what kind of phenomena will we discuss? So we already mentioned that we will discuss quantum magnetism, and we have at least two main forms of quantum magnetism. There are also others. But here in this talk, I will discuss about antiferromagnetic phases, where if you have, let's say, spin 1/2 particles, okay, you can imagine that the spins will organize themselves so that you have a spin down, a spin up, and spin down, and spin up. Okay. And we will discuss this phenomenon in the context of one-dimensional Fermi gases in optical lattices. Okay? So the presence of this periodic potential will help this kind of antiferromagnetic arrangement. Okay? But we might also have a ferromagnetism. Okay? Now in this context, in these experimental setups, they are a bit particular because in these systems, the numbers of spin-up and spin-down particles, they are separately conserved. Okay? This is a bit different compared to electronic systems where the spins can flip. So here in this context, ferromagnetism means that you have a sort of phase separation by the particles with spin up, which separates from the particle with spin down. Okay? And we'll discuss this phenomenon in the context of three-dimensional Fermi gases. So now let's go to methods. So let me say a few words about quantum Monte Carlo methods. I will assume that you know, you're not very familiar with quantum Monte Carlo. So there are two main families of quantum Monte Carlo techniques. The first one, I mean, they're mostly methods that work at finite temperatures, and they're based on path integrals. Okay, so they're called path integral Monte Carlo. They're actually methods which are based on the idea that you can map a quantum system in D dimension to a classical system in D+1 dimensions. Okay? So at the end of the day, what you do is do this mapping, and then you perform classical Monte Carlo on the D+1 dimensional system. Okay? So these kind of methods are sometimes called classical Monte Carlo on steroids. Okay? So they're very nice and very powerful because you can use all of the tricks that we have already discussed in the workshop to speed up your Monte Carlo simulation. So everything you learn from classical Monte Carlo, you can import that into the realm of quantum Monte Carlo. Okay? You just have to apply the technique to a system in D+1 dimension. Okay? So for example, if you're interested in a quantum ISM model in 2D, you have to simulate a classical ISM model in 3D. They're extremely useful because they can work at any finite temperature. Okay? The drawbacks is that their computational cost increases as you go to lower and lower temperatures. And it diverges at 0 temperature. Okay? So in many cases, we are interested in studying systems at extremely low temperatures, in the context of cold atoms, but also in electronic systems. And so this kind of computational techniques might be problematic. So sometimes it is instead better to forget about temperature and to decide to study the ground state of the system. Okay, so what you have at exactly 0 temperature. Okay, you can do that with what here I call projective quantum Monte Carlo methods. Okay, there are different kinds of projective methods. Some are called Green's function Monte Carlo, some are called diffusion Monte Carlo, but there is some confusion sometimes about the names. Okay, I will describe this kind of methods and give you an intuitive idea of how they work. But let me already say that so they are based on the idea that you have to solve the Schrödinger equation, but with an imaginary time. They're a bit particular because in this case, what you're trying to sample is the ground state wave function, but the ground state wave function is a function you don't know. Okay? So they're a bit different compared to classical Monte Carlo, because here you have to sample function that you don't know how to compute it or evaluate it in polynomial time. Okay? So it's the Schrödinger equation that gives you the Monte Carlo algorithm. But if you're trying to sample a function that you don't even know. So you cannot use all of the tricks that you learn from classical Monte Carlo, because the algorithm is given by nature. But you have different tricks to enhance the efficiency of the algorithm. You do that with what we call trivial functions. Okay? The limitation is that they only work at 0 temperature. Okay? So they do not allow you to study finite temperature phase transitions. By the way, I know that Tommaso Macri will give a talk where he will present methods based on path integral Monte Carlo on Friday. So if you are interested in the first kind of methods, maybe you should listen to his talk. So I will not describe them. I will switch directly to describe projective methods. So I will present one of these methods, which is called Diffusion Monte Carlo. So the idea is to take the time-dependent Schrödinger equation and to replace the time with an imaginary time. Okay? And so you get an equation which looks a bit similar to a diffusion equation. Okay? With the difference which you have this additional term which plays somehow the role of a source and sink term. Okay? Why do we like the Schrödinger equation in imaginary time? Well, see what is the effect of this imaginary time evolution. Let's imagine that you start from an initial state, which we call psi. You want to determine the state at a later imaginary time tau. So you have to apply this imaginary time evolution operator. If you expand this initial state on the basis of the eigenstates of the Hamiltonian, which is what is done here, you can see that after a very, very long time, you can neglect all of the excited states because they are multiplied by an exponentially small number. Okay? And so after a very, very long time, you get the ground state. Okay? So if I'm able to solve this Schrödinger equation in imaginary time, I can get information about the ground state. Okay? Here, this ERF is a reference energy which has to be chosen appropriately, but I will not discuss this detail. So in practice, so what is interesting here is that and I will explain you how to do it, we can solve stochastically this equation because, as we said, it looks like a diffusion equation. That's why the method is called Diffusion Monte Carlo. Now, the method has to be improved to make it efficient enough for a realistic system. And we do that by doing a special kind of importance sampling. Okay? It's a special importance sampling because what you do here is to introduce what we call trivial function, psi t, which has to be a decent approximation for the ground state wave function. Okay? Something that if you know a little bit of physics, of quantum physics, you can always write down. Okay? And so you introduce this function f, which is the product of your ansatz times time-dependent wave function. And then you substitute this into the original imaginary time Schrödinger equation, and you get a modified Schrödinger equation, which is kind of similar to what we had before, but it has this additional term, which plays the role of a drift force. Okay. Now this equation is nice because we can write down a decent, well, actually a very accurate approximation for the Green's function of this system. Approximation which becomes exact for short time steps. Okay, I'm not writing the explicit formula here. I describe it in words. So at the end of the day, what you have to simulate is a Monte Carlo simulation where your algorithm is very simple. You have to alternate 3 steps. The first one where you simulate a random Gaussian diffusion. Okay. Then you have to take into account this deterministic drift force. So you move your particle according to a deterministic force that you can compute. But then you have to introduce what is usually called branching, but it's maybe more intuitive to call it cloning or killing algorithm. So what you must have is a large population of random walkers. And we have already heard enough about random walkers. So you have many copies of your systems, you evolve them according to these 3 steps, but then sometimes you have to kill some of these copies, okay, so you kill the walkers, or you replicate them, okay, according to a specific algorithm that I will not describe in detail, okay. So by evolving stochastically this large population of random walkers, you can emulate this modified Schrödinger equation in imaginary time, and at the end of the day, sample something which is proportional to the ground state wave function. Okay. Now, what I've said so far applies to quantum system, but I didn't say anything about symmetry. Okay. But to say about the statistics of the particles. So, are we dealing with fermions or with bosons? Okay. So everything we described was defined in the coordinate representation, but this is a basis which knows nothing about the symmetry of the state, which means that with this projector in imaginary time, we will get the ground state. So the state with the lower, is a question? No, we have trajectories. So we are simulating many walkers. Say it again? Why not? Yes, we have. Yeah, for this moment, forget about quantum mechanics. Look at this equation. So it's a diffusion equation. Okay. So I can simulate particles which diffuse. Okay. If I didn't tell you that this is quantum mechanics, then you will call this. If I didn't tell you that this is quantum mechanics, you will take this and you call it diffusion equation. Okay, there is this additional term, which gives this. Well, actually, it's the term which is responsible for this killing multiplication of walkers. Okay, so it's a combination of a diffusion and a genetic algorithm. Okay, but at the end of the day, you sample this. That's what we want to compute ground state properties. So here we are just looking at the similarity between quantum mechanics and something which you could have also in classical physics. But as I said, you get the state with the lowest energy, okay? And under very general conditions, this turns out to be a state which is symmetric under particle exchange. Okay, so it's a bosonic state. Okay, but sometimes we want to study fermions, okay? And with fermions, we have the constraint that wave function has to be antisymmetric under particle exchange, okay? So the state with lowest energy among those which are antisymmetric is actually an excited state if you consider the full Hilbert space. So how do we get information about fermions? Okay? So what you call is what is called fixed node approximation. Okay? So you might have to introduce an approximation, unfortunately. So the idea is to introduce what is called the nodal surface. Okay? This is a dn minus one dimensional hypersurface. So think about your configuration space. This is the dimensionality of the system. So we have a dn dimensional space. And we can define a hypersurface in this space, which is fixed by the condition that the wave function is equal to 0. Okay? And this hypersurface separates the configuration space into what are called nodal pockets. So they're pockets where the wave function has a fixed sign. Okay? Inside each nodal pocket, the wave function is either positive or negative. Okay? So the idea is to impose a fixed node constraint. So we force the wave function of the system, okay, to have the nodes, the same nodes of our variational ansatz, a tri-wave function. Okay? So the product of this tri-wave function and the actual ground state that we will get is everywhere positive, okay, because the two functions change sign together. Okay? So inside each nodal pocket, we can use the diffusion Monte Carlo to get the ground state, because now inside the nodal pocket, the sign is fixed. Okay? We don't have a sign problem. Okay? So why is this method useful, despite the fact that we have introduced a constraint? Yes? No. So this hypersurface is defined by this condition. Okay? Is the set of points where the ground state is equal to 0. No. So in certain points, it's not everywhere 0. Only in certain points of the Hilbert space. Okay. So here, this is not value for all. This is not true for all points in the coordinates. It's only true for the points in the configuration space which belong to the nodal surface. Okay. So this nodal surface is defined by this condition. Okay? It's not zero everywhere, it's zero in certain points. It has to be zero in certain points because it has to change sign. It's a fermionic wave function. So how can we use this method? So it can be used because we can prove that the results that you obtain with this constraint, okay, it's not exact, but it's a rigorous upper bound. So you get an energy which is always above the true ground state energy. And so the problem can be translated into an optimization problem. Okay? So you have to change the shape of your nodal surface in order to optimize the state and get the lowest possible energy. It can be proven that if you know the exact nodal surface, then you get the exact result. Okay? But in general, this may introduce a systematic approximation. So what we will use later on is the fact that in dimension equal to 1, so only one dimension, we do know the exact nodal surface. Okay? This was proven by Separately in 91. So in D equal 1, the nodal surface coincide with what are called the coincidence points, which are the points where two identical fermions are on the same point. Okay? So in 1D, with this kind of approach, we can obtain exact result. So let us consider first one-dimensional systems. Okay? So with cold atoms, in the experiment with cold atoms, people use optical lattices to create quasi-one-dimensional systems. So you use two pairs of counter-propagating laser beams. Okay, so a 2D optical lattice. And if these two optical lattices are very, very strong, you can create very tightly confined 1D tubes. Okay? And if the strength of the radial confinement is such that the typical energy scale of this confinement is much larger than any other energy scales, in particular the temperature, then the motion in the radial direction is frozen. You can describe this gas as being kinematically one-dimensional. Okay, so the motion is confined along 1D. Okay, so we'll describe, we'll consider a very simple Hamiltonian. It's a 1D Hamiltonian, purely 1D system, where we have a kinetic energy, and we have an external potential which is designed to describe a longitudinal optical lattice. So we have quantum particles which move in a periodic potential, described by this sine squared function. And the interaction will be a contact interaction. Okay, so we will have interaction where two fermions with opposite spin touch each other. Okay, and the parameter of this interaction strength, this parameter G, can be related to the physical parameters of the actual experimental system. Okay, so G is given by this formula here, where you have this parameter A1D, which can be computed with this formula, where you have the 3D S-wave scatter length, okay, which is given by the experimentalist, and this parameter, which is here, it is called A-porp, which is the typical size of your tube in the transverse direction. Okay, and this formula was proven a few years ago by Olshani. Here, this is a reference. So we can exactly map the experimental setup, okay, this kind of system, to this Hamiltonian. So as I said, we consider one-dimensional systems with a longitudinal optical lattice. And if the optical lattice has zero intensity, then we have just a 1D homogeneous Fermi gas. Okay, but then we can turn on the optical lattice and make it, well, at first it's shallow, so we have quantum particles in a very weak periodic potential, and then we can make it more and more intense. And at the end, we have a very deep periodic potentials. And here we can introduce a basis of localized orbitals. They're called Wannier functions. And if the band gap between the lowest band and the first excited band is very, very large, then we can introduce a one-dimensional discrete lattice model, which is called the Hubbard model. Okay? So here we have two models in the two extreme regime, the homogeneous Fermi gas and the 1D Hubbard model. In the Hubbard model, you have these two energy scales, the hopping energy, which describes how much particles like to jump from one side to the other, and the interaction parameter U, which gives the energy that you pay when two fermions are on the same side. And both of these parameters can be computed exactly, and the mapping to this discrete model becomes more and more accurate as the optical lattice becomes deeper and deeper. Okay? These two models are quite interesting because there are exact solutions for these two models. Okay? So they're models that play essentially the same role in the physics of quantum many-body system as the classical ISM model in the physics of classical statistical mechanics. Okay? And as for the ISM model in 2D, you have the Onsager exact solution. Here we have two exact solutions for the properties of both the homogeneous Fermi gas and the Hubbard model. But here with our diffusion Monte Carlo technique, we want to get exact results, not only in the two extreme limit, but all the way from one regime to the other. So here we have a comparison between the two exact theories. Okay? So here with the homogeneous Fermi gas, what we plot is the interaction energy, so it's the energy of the ground state minus the energy of a non-interacting Fermi gas as a function of a dimensional interaction parameter. Okay? So in black, you have the exact results, which was obtained by using the Bethe-Ansatz theory by Young. And you see that indeed when the optical lattice has zero intensity, so we are simulating indeed a homogeneous Fermi gas, our diffusion Monte Carlo results perfectly reproduce the Bethe-Ansatz theory. Okay? And then we can go to a very deep optical lattice and map the system to a one-dimensional Hubbard model. And here again you have the result, the interaction energy as a function of the Hubbard interaction parameter U. And you see that as the optical lattice becomes deeper and deeper, our data do indeed approach the exact ground state energy, which was computed first by Lieb and Wu for the 1D Hubbard model. So we can see that indeed this diffusion Monte Carlo in 1D, even though you have to circumvent the sign problem using this fixed node approach, but in 1D it does not introduce any systematic error. Okay? So what we did here was to study the emergence of antiferromagnetism. Okay? So here we are considering, oops, I went too far, no. We are considering a commensurate optical lattice, so a 1D system with a periodic potential where the density is such that on average there is one fermion per well. Okay? I want to see the emergence of this kind of spin ordering. Okay? And we do that by computing the static dynamic structure factor, which is shown here. And here we have different data sets. First, by fixing the intensity of the optical lattice and vary the interaction strength. And you see this peak, which emerges, which clearly shows the emergence of antiferromagnetic correlations. Okay? And again, you can also induce antiferromagnetism by fixing the interaction strength, okay, and making the optical lattice deeper and deeper. Okay? So now the question is whether this antiferromagnetism has really a long-range order or not. Okay? Actually, we know that there cannot be true long-range order in one dimension. Okay? This is due to the Mermin-Wagner theorem. And so what we did was to analyze how the height of this peak, okay, varies when we vary the system size. Okay? And what we see is that there is a very slow divergence, okay, which is consistent with a logarithmic divergence. Okay? This is what indeed we expect, because in 1D, in the Hubbard model, it is known from conformal field theory that the antiferromagnetic correlations have a quasi-long-range character. So the decay is in an algebraic way. In particular, the decay is 1 over distance. Okay? And since the decay in real space is 1 over distance, okay, in the structure factor, you should observe a logarithmic divergence. Okay? Here the system sizes are very small to make a strong claim about logarithmic divergence, but at least we can claim that there is consistency. So I'm a bit running late, so I will go very fast about this part. So we also consider a 3D repulsive Fermi gas. Here we model interaction with a very simple hard sphere model, but I will not discuss the detail. So what we want to see is whether there can be a ferromagnetic transition, It is sometimes called Stoner instability. The mechanism is very easy. So the idea is to the fact that if you have a strong interspecies repulsion, so strong repulsion between spin-up and spin-down particles, the system at some point might prefer to have a sort of phase separation. This will give an increase of the local Fermi energy, so the kinetic energy increases, but you have a strong reduction of the interaction energy due to the fact that identical fermions do not interact when the interaction has a short-range character. Okay? Because of the Pauli exclusion principle prevents two identical fermions to get very close to each other. Okay? Now, it is not yet clear whether this transition is supposed to take place at all. Mean field theory do predict that it has to take place when the interaction parameter, which here is written as KFA, KF is the Fermi momentum, A is the S-wave scattering length. When this parameter has this value, there should be a transition according to mean field theory, but we don't know whether we should trust mean field theory. So we perform the quantum Monte Carlo calculations, but here we are using this fixed node approximation. So in 3D, we are not guaranteed to get the exact result. Okay? But if you do this diffusion Monte Carlo within this fixed node approximation, you get that indeed a transition should take place, but at the critical value of the interaction strength, which is much smaller than what is predicted by the mean field theory. Okay? And the critical point here was computed by computing the magnetic susceptibility. Here we plot the inverse of it, and we see that it goes to 0. And this marks the critical point of the transition from a paramagnetic phase to at least a partially ferromagnetic phase. What we know is actually that then there is a second critical point where the system becomes fully ferromagnetic. Yeah, of course. Yeah, the nodes have to be adjusted. So the nodes are different depending on the phase. Okay. Yes. So there is a. So the main part of the work is to optimize the nodal surface, and different phases have different nodes. Okay. But then you use a variational approach to determine which. You have to see which phase has the minimum energy. And that is your estimate for the ground state. So an experiment to confirm whether this transition is supposed to take place was performed very recently in Florence at Lens. And they use what is called the upper branch of a Fishbach resonance to create a strongly repulsive three-dimensional Fermi gas. Now, the system is actually experimentally in the experiment, it's unstable against molecule formation. So to circumvent the problems due to molecule formation, what they did is to create an artificially already ferromagnetic phase, so a phase where the spin-up and the spin-down particles have separated, and they have studied the stability of these two separated clouds. In particular, what they did was to measure. So what it is to create these two separated clouds. They have introduced a barrier between them, and they have then slowly removed this barrier. And they have seen is that if the interaction strength is not very strong, the two clouds start merging, but then they also start oscillating out of phase. Okay, so you have a spin dipole mode, and they have measured the frequency of this spin dipole mode. And they've seen that this frequency decreases as a function of the interaction strength. But at some point, it jumps up when the repulsion is very strong. And what happens here is that the two clouds remain stable in the fully ferromagnetic phase. Okay? So the two clouds do not start merging at all. Okay? And this frequency corresponds to the frequency of the two clouds oscillating by hitting against each other. Okay? And this critical point corresponds very well with what the quantum Monte Carlo prediction, with what the quantum Monte Carlo simulations predicted. Okay? So here we can say that despite of the fact that we have to use this fixed node approximation, it seems that it's a good enough approximation to describe this kind of ferromagnetism. Okay? So in the last part of this presentation, now if you were lost in the first part, if you were not interested, you can jump in and follow the second part. I will change a bit the topic. I will go fast because I don't have much time. I will start discussing about adiabatic quantum computing, okay? In particular, about solving optimization problems via a phenomenon which is called quantum annealing. Okay? So during this conference, we have already heard about optimization problems, so I don't have to spend much time to convince you that they appear in many branches of physics and engineering. So I can actually skip the slide. You probably already know that the difficult optimization problems, the ones that you always encounter, they are characterized by a very rough energy surface, an energy landscape that you have to explore, okay? And you want to find the absolute minimum, okay? And we already heard during the conference that there is one possible computational technique which you can use, which is called simulated annealing. And the idea is very simple. You perform a classical Monte Carlo simulation, and you slowly reduce the temperature during your simulation. Now, why is this useful? It is useful because the thermal excitations that you have at the beginning of the simulation, when the temperature is high, they can help you to jump from local minima above the barriers, and hopefully, at the end of the simulation, you wish to reach the global minimum. Okay? So now here the idea is that we might introduce quantum effects. Okay? And they might help because if we have very high energy barriers, it might be more convenient to tunnel through the barrier rather than jumping above it. Okay? So we can already understand that maybe quantum mechanics can help us in solving optimization problems. This can be formalized a bit better. So let's consider, for example, the typical case which is considered in the field of machine learning, which is what physicists will call the ISM model. Actually, the ISM glass. So here we have an ISM glass Hamiltonian, where we have our spins, sigma z, which at the moment they are classical variables, which are either plus or minus 1. And we have couplings, okay, which are j, ij, which define the optimization problem that you want to solve. Okay? But you can think of them as, let's say, random variables. Okay? And here the idea of quantum annealing, or alias adiabatic quantum computing, is to introduce quantum mechanics. And you do that by introducing a transverse field, a transverse magnetic field. Okay? So now the sigma become Pauli matrices, and the transverse field is described by sigma x. Okay? And this transverse field introduces quantum fluctuations. Okay? So the idea is to perform quantum annealing. So what we think is that at the beginning of our annealing process, this transverse field very, very strong. Okay? So the ground state of this quantum, which now it's a quantum Hamiltonian, is trivial. All of the spins align with the transverse field. And then what we do is to slowly reduce the transverse field, and at the end of your annealing, the transverse field is exactly equal to 0. Okay? So now we have already completely killed this quantum term. We are left with the original classical problem. Okay? And the idea is that if we do the process slowly enough, we will stay in the ground state of this quantum system. Okay? And there is a theorem, the adiabatic theorem, that tells us how slow we have to do the process in order to be guaranteed that we remain in the ground state. Okay? And we know that this annealing time, it's called here T fin, has to scale with a constant, which is not interesting for us, divided by delta squared. Delta is the smallest energy gap that you encounter during your quasi-adiabatic or adiabatic process. Okay? So we see is that if there is a very small gap, then the computation here is not very efficient because we need a very long time. Okay? So remember this 1 over delta squared scaling because it will be important later on. Okay? Now, if the research funds in your institute go up, then you might consider buying a quantum computer which is supposed to solve optimization problems using this kind of approach. You can buy it from a Canadian company which is called DWave. And they have built a machine which is supposed to be a physical realization of the quantum ISM model. It's a machine where you can program the values of these couplings. And you can also vary the value of this transverse field and perform an annealing process. Okay? I will not describe the technology. Here I only show the graph that you are able to realize. So hopefully, what you would like to have is a graph with the highest possible connectivity, such that you can realize, you can implement the most complicated optimization problems. In practice, what they have is what is called a chimeric graph, which is a reasonably sparse graph, but at least it is non-planar. This is somewhat important. So the questions that we can ask is whether this kind of adiabatic quantum computer may or may not outperform any classical algorithm that we can use on our classical computers to solve optimization problems. Okay. You can understand that it's not easy to answer this question, and the reason is that in order to give a definite answer, what you should do is to simulate the real-time dynamics of this model. Okay? And you probably know that simulating the real-time dynamics of quantum system is an extremely challenging problem. Okay? Now, the commercialization of this machine made some noise, so it was in the covers of glossy journals. And I like the title of The Economist, because here they were making reference of the debate about whether this machine is actually faster or slower than classical computer, and the title have faster, slower, or both at once, which is a nice way to describe what a Schrödinger-Katz state is. So what are the questions which are interesting for us? So again, the main question is whether a quantum device of this kind can outperform any classical optimization method. And the question which is interesting for us is whether quantum Monte Carlo simulations that we can run on a classical laptop, they can be used to give some hint about the answer to this question. Yep. So what do we do? So as we said, in principle, when you want to solve an optimization problem, you could simulate, you could perform simulated annealing. Let's call it classical simulated annealing with classical Monte Carlo, for example, using the Metropolis algorithm. But we can also do simulated quantum annealing. Okay? So the idea is that instead of using classical Monte Carlo, we use quantum Monte Carlo. And we do our quantum Monte Carlo simulation performing a quantum annealing process. Okay? So we do our Monte Carlo dynamics. We start with a very strong transverse magnetic field, so with very strong magnetic fluctuations. And during the simulation, we reduce the transverse field, and we kill the quantum fluctuations. And then we can ask the question whether we find or we don't find the true minimum, the absolute minimum. Okay? So now the question is whether this pseudodynamics of the quantum Monte Carlo simulation has anything to do or not with the real-time dynamics of a DWave machine, for example. Okay? So usually the dogma is that the dynamics of Monte Carlo contains no information, and we don't even look at that. But in this field, you have to ask the question whether there is any relation, and it is important to understand whether indeed a quantum device like the DWave quantum computer can be better and more efficient than the fictitious dynamics that you can perform using a quantum Monte Carlo. Because if it's not, then the quantum computer is useless. Okay? You can just run your quantum Monte Carlo algorithm. So as we said before in the first part, there are two ways to main families of quantum Monte Carlo methods. And here again, you can do, for example, path integral Monte Carlo. Suppose that you want to simulate a 2D ISM model, then you just map it to a 3D ISM model, and you perform classical Monte Carlo on this or this three-dimensional system. And what some scientists, these guys here, have investigated is whether this, if you use the path integral Monte Carlo as an optimization method, whether you get results which do look similar to what you will get by running the calculation on DWave quantum computers. Okay, so these guys had access to one of the DWave quantum computers, and they found that there is a very strong similarity. Okay, so what they did is to choose a large number of possible optimization problems, and they performed many runs. They have computed an histogram on how many times the algorithm did find the exact solution. Okay? And what they've seen from this histogram is that there is a very strong similarity between the behavior of the DWave device and the simulated quantum annealer. Okay? So what you obtain by using the quantum Monte Carlo simulation. In particular, they have seen that both on with quantum Monte Carlo and on the DWave machine, you have many instances which are very difficult, so you have a very low probability to get the exact solution. And then you have also many instances which are very easy, so you often, almost always obtain the exact solution with probability close to 1, and very few in between. Okay? While if you do classical Monte Carlo, okay, so you do classical simulated annealing, you obtain a completely different distribution. Okay? Indeed. Yeah, indeed, this is a very strange result. And they also analyzed the fact that not only there is this similarity, but also the instances which are easy or hard are the same with very high probability. Now, to understand this point better, which indeed looks a bit mysterious at first sight, so these guys consider that a very simple quantum model. So they considered a ferromagnetic ISM chain. So now it's a 1D ISM model, quantum ISM model, with all couplings to be equal and negative. Okay? So we know that in this case, if gamma is small, then there are two competing solutions, the one where the system has magnetization up and the one with magnetization down, and they are separated by an energy barrier. Okay? And what they did is to analyze how fast the Monte Carlo, the quantum Monte Carlo, can go from this situation. Suppose that at the beginning of your simulation you start here with all your spins down. How much time, how many quantum Monte Carlo steps it takes to find your system in the other well. Okay? And they call this quantum tunneling time. Okay? And they have analyzed how this quantum tunneling time, how it varies with the size of the system. Okay? And they have seen this kind of behavior. So here you see, actually probably you don't even see, there are two data sets that are both open symbols and closed symbols. Okay? And the closed symbols represent actually 1 over delta squared, okay? Where delta is the gap. So this is the scaling that we discussed before, and it's the computational time that a quantum annealer that performs the optimization in real time will need to find the exact solution. Okay? So they see that the scaling, the tunneling time of the quantum Monte Carlo scales exactly as 1 over delta squared. Okay? So there is a very strong similarity between the computational scaling that you expect from a real-time quantum annealer and the tunneling time of the quantum Monte Carlo simulation. And if you perform this path integral Monte Carlo using the open boundary condition in imaginary time, you get an even better scaling. So instead of 1 over delta squared, is 1 over delta. Okay? So you may think that, so if you do this modified quantum Monte Carlo, you get an even better scaling. So here the quantum Monte Carlo seems to scale better than what a quantum computer will do. Okay? So 2 employees of this company, DWave, they tried to invent a more difficult, challenging problem, and they introduced this model, which is called Shamrock. It's the minimal model that contains some sort of frustration. Okay? So here you have these leaves, and here you have pairs of spins which have an antiferromagnetic coupling, and they all interact ferromagnetically with the central spin. Okay? And again, even in this model, you have two competing solutions, so the state can be all up or all down. And they've seen that in this case, the path integral Monte Carlo has a very bad scaling. Okay? So instead of going 1 over delta squared, you have 1 over delta squared, but with this coefficient which depends on the size of the system. Okay? This 2 to the k, where k is the number of leaves. Okay? While the computational time of the quantum annealer will be only 1 over delta. Okay? So in this case, this is a different kind of still simple but more challenging optimization problem. In this case, indeed, a quantum annealer will defeat path integral Monte Carlo. So what we did instead is to implement a projective kind of quantum Monte Carlo for the same model. I will not explain how it works because I don't have time. And what we have seen is that if you do diffusion Monte Carlo instead of path integral Monte Carlo, not only you don't have this pathology of the dynamics of the path integral Monte Carlo, but you still can defeat the scaling of the quantum annealer. Okay? So instead of 1 over delta squared, we have 1 over delta. Okay? So even in this slightly more challenging problem where there is some frustration, the expected dynamic of an adiabatic quantum computer is not better than what you could do using a quantum Monte Carlo algorithm on a classical computer. Okay? So my time is over. I will just conclude by quickly summarizing. So in the first part, we discussed the properties of atomic Fermi gases, and in particular the emergence of quantum magnetism. We have seen it in 1D. We can study the emergence of antiferromagnetic correlations. Okay? In 3D, we have used this fixed node approximation to study the emergence of ferromagnetism at strong repulsive interactions, and we have seen that there is agreement with between the Monte Carlo predictions and the recent experiments performed at Florence. And then we discussed in the second part about adiabatic quantum computing, and I hope I have convinced you that quantum Monte Carlo simulations, in particular the projective kind of quantum Monte Carlo simulation, can give us some information of if and where adiabatic quantum computers can defeat classical optimization algorithm. And with this, I thank you very much for your attention.